The concept of a self-charging electric vehicle captures the imagination of both consumers and engineers. It promises a future where the inconvenience of plugging in disappears entirely. Proponents envision cars that continuously replenish their batteries while in motion or at rest. This vision suggests an era of unlimited range and near-zero downtime. Such possibilities inspire intense research and substantial investment across the globe. The race is not just technological but also geopolitical. Nations see leadership in self-charging EV technology as a pathway to economic and strategic advantage. Car manufacturers frame it as the next great leap in automotive history. Investors see a potential goldmine that could disrupt energy markets forever. However, the realities of engineering such a machine remain far from simple. Physics imposes unavoidable constraints that marketing rarely highlights. Energy must come from somewhere, and self-charging cannot defy the laws of thermodynamics. Many proposed systems involve integrating renewable energy generation directly into the vehicle. Solar panels on the roof and bodywork are among the most common ideas. Some prototypes even use solar skins that conform to the curves of the car. These designs are visually striking and suggest technical sophistication. Yet the actual energy harvested from such panels is often modest. An average car roof can only accommodate a few square meters of solar cells. Even with high-efficiency panels, the daily energy yield is limited. In optimal sunlight, this might add tens of kilometers of range per day. For many drivers, that is insufficient to replace traditional charging entirely. Weather, latitude, and seasonal changes further limit solar reliability. A self-charging EV relying solely on integrated solar cannot yet match consumer expectations for convenience. Researchers are exploring kinetic energy recovery as another avenue. This builds upon existing regenerative braking systems already present in modern EVs. In theory, regenerative systems could be enhanced to capture more than just braking energy. Some proposals involve harnessing vibrations, suspension movement, or even airflow. The challenge is that these sources yield minimal power compared to driving needs. Air turbines, for example, add aerodynamic drag that offsets their gains. Harvesting energy from motion inevitably reduces efficiency somewhere else. This trade-off makes perpetual motion through self-harvesting impossible. Wireless charging is another area of interest in the self-charging conversation. Dynamic wireless charging systems embed coils beneath road surfaces. These coils transfer power to a moving vehicle through inductive coupling. If deployed on highways, they could top up EV batteries continuously. Such infrastructure would effectively turn roads into charging stations. However, the cost and complexity of installing such systems are staggering. Maintenance challenges arise from embedding sensitive electronics beneath asphalt. There are also interoperability concerns between different manufacturers. Standards would need to be agreed upon at a global level. Political will and public funding are essential for such massive projects. Private companies may hesitate to invest without guaranteed usage. Urban planners would face the challenge of retrofitting existing roads. Meanwhile, battery technology continues to evolve in parallel with charging innovations. Some researchers argue that improving energy density and charging speed is more practical than self-charging. High-capacity batteries combined with ultra-fast chargers could offer similar convenience. Such an approach avoids the inefficiencies of constant self-harvesting systems. Still, the allure of a car that charges itself remains strong. Consumer psychology plays a large role in sustaining the hype. The idea taps into a broader cultural fascination with autonomy. It also aligns with a desire to reduce dependence on infrastructure. Marketers leverage this narrative to build excitement and attract investors. Media outlets often amplify optimistic claims without sufficient technical scrutiny. This creates a feedback loop of expectation and speculation. The gap between promise and reality widens as a result. When early prototypes fail to meet exaggerated claims, public trust can erode. This cycle has been seen before in other emerging technologies. Hydrogen fuel cell vehicles went through a similar hype curve. Early visions promised rapid adoption and minimal barriers. In practice, infrastructure and cost challenges slowed progress dramatically. Self-charging EVs could face a comparable trajectory if realities are ignored. Industry leaders acknowledge these challenges behind closed doors. Publicly, however, optimism remains a core part of the messaging. This tension between engineering reality and marketing ambition defines much of the field. Academic researchers play a key role in bridging the gap. Their work tests the limits of materials, energy conversion, and integration. Peer-reviewed studies often reveal performance figures that differ from press releases. For example, one solar-integrated EV prototype produced less than half the range claimed in promotional materials. These discrepancies may result from testing in controlled, ideal conditions. Real-world driving introduces variables that reduce efficiency. Temperature fluctuations can affect both solar cells and batteries. Dust, dirt, and shading from nearby objects further cut energy harvest. Engineers must account for these losses in practical designs. The race for self-charging EVs is not purely about technology. Policy and regulation influence the pace of development significantly. Governments can accelerate adoption through subsidies and research grants. They can also hinder progress with conflicting standards or unclear rules. International cooperation is particularly important for technologies that cross borders. An EV designed for dynamic wireless charging in one country should work abroad as well. This requires agreements on frequency, power levels, and safety protocols. The European Union has begun preliminary discussions on such harmonization. In Asia, Japan and South Korea have launched pilot projects for on-road charging. These trials test both technical feasibility and public reception. Public perception is shaped by more than just raw performance data. A vehicle that visibly charges itself while driving could inspire enthusiasm. The symbolic value may outweigh the actual energy contribution. This could lead to niche markets for partially self-charging EVs. Luxury brands might adopt the feature as a status symbol. Fleet operators might use it to signal environmental responsibility. Marketing potential alone could justify partial integration of self-charging elements. Even if the technology cannot fully replace plug-in charging, it could reduce frequency. Reducing the need for charging stops by even 20% could be attractive. This is especially true for delivery vehicles or taxis that operate all day. Any technology that increases uptime has economic value for such fleets. Yet for private owners, the cost-benefit calculation is different. The added expense of self-charging hardware may not pay off in fuel savings. Solar panels, turbines, and advanced regenerative systems increase manufacturing complexity. They can also add weight, which reduces overall efficiency. Maintenance of these systems could further add to lifetime costs. Manufacturers must balance innovation with affordability. Mass market adoption depends on keeping prices competitive. Some companies may focus on high-end models first to absorb development costs. Over time, successful features could trickle down to mainstream vehicles. This mirrors the trajectory of many automotive technologies in the past. Anti-lock brakes, airbags, and hybrid drivetrains all began in premium segments. Scaling production reduces costs and improves efficiency. Whether self-charging systems can follow this path remains uncertain. Consumer demand will play a decisive role in determining the answer. Some experimental vehicles are exploring hybrid self-charging concepts. These combine multiple small-scale energy sources into a single integrated system. For example, a car might use solar panels for daytime charging and wireless charging pads in parking spaces at night. This approach spreads the risk of relying on a single technology. It also increases the overall probability of capturing some energy in most conditions. However, integration complexity rises with each added component. Software must manage energy flow between various inputs and the main battery. Hardware must withstand environmental conditions ranging from heat to snow. Electrical safety becomes more challenging when multiple power sources are connected. Redundancy in safety systems may be required, increasing costs further. Still, engineers are optimistic about incremental progress. Small steps toward self-sufficiency can eventually add up to significant gains. One example is the steady improvement of photovoltaic cell efficiency. Laboratory tests have produced solar cells with over 40% efficiency. Commercial cells in mass production are still far lower, but gains are coming. As efficiency improves, smaller surfaces can produce more energy. This opens possibilities for more discrete integration into a car's surfaces. Transparent solar films could be applied to windows without obstructing visibility. Curved solar modules could be molded into body panels seamlessly. These advances would allow designers to maintain aesthetics while adding function. Automakers value appearance as much as performance in consumer markets. Even high-efficiency solar will still face limits set by the sun's energy. This makes it unlikely that self-charging will ever be entirely independent of external infrastructure. Nonetheless, partial autonomy can still be valuable. A commuter who drives short distances daily might rely solely on solar charging in summer months. In such cases, plug-in charging could be reserved for longer trips. This would extend the lifespan of charging equipment and batteries. Reducing deep discharge cycles can improve battery longevity. Longer-lasting batteries have both economic and environmental benefits. Fewer replacements mean lower lifetime ownership costs. They also reduce demand for raw materials like lithium and cobalt. Mining for these materials carries significant environmental and social costs. Therefore, even modest self-charging capabilities can contribute to sustainability goals. Governments and NGOs may highlight this as part of climate strategies. Policy incentives could target cars with integrated self-charging systems. Tax credits or rebates could offset the initial cost for buyers. Automakers could receive subsidies for incorporating renewable energy generation in vehicles. Such measures could accelerate adoption, even if technology remains imperfect. The question remains whether consumers will value these benefits enough to influence buying decisions. Market research shows mixed signals. Some buyers prioritize environmental features heavily in their purchasing choices. Others focus primarily on cost, performance, and convenience. Self-charging technology must deliver tangible benefits in at least one of these areas to succeed commercially. Purely symbolic or novelty value may not sustain long-term sales. Still, niche markets can provide important stepping stones toward mainstream adoption. Early adopters often act as ambassadors for emerging technologies. Their enthusiasm can shape public perception and drive awareness. Media coverage of unique or futuristic vehicles amplifies this effect. Concept cars play a major role in maintaining excitement. Auto shows often feature striking prototypes with dramatic self-charging elements. These may include retractable solar wings or transparent photovoltaic roofs. While these features may never enter mass production, they keep the conversation alive. They also provide valuable testing grounds for new materials and engineering approaches. Lessons learned from concept vehicles often inform later, more practical designs. Consumer expectations can be shaped gradually through exposure to these ideas. The challenge is to avoid over-promising and under-delivering. History is full of technologies that suffered from premature hype. If consumers feel misled, they may reject future offerings regardless of improvements. Automakers and researchers must balance ambition with realism. Honest communication about limitations builds credibility. It also helps align public expectations with achievable outcomes. For example, framing self-charging as a range extender rather than a full replacement could prevent disappointment. This would position the technology as a complement to existing charging methods. Hybrid approaches combining self-charging with high-speed plug-in systems could provide the best of both worlds. Such combinations may offer practical advantages without requiring revolutionary breakthroughs. In the long run, incremental adoption might outpace attempts at sudden transformation. Gradual improvement also allows supporting industries to adapt. Charging infrastructure providers can integrate wireless pads alongside plug-in stations. Solar manufacturers can develop modules optimized for vehicle integration. Policy frameworks can evolve alongside technical capabilities. These parallel developments reduce the risk of stranded investments. Meanwhile, research into energy storage continues to advance rapidly. Solid-state batteries promise higher energy density and faster charging times. They may also tolerate partial charging cycles better than current lithium-ion cells. Such characteristics would complement self-charging systems perfectly. The ability to store small trickles of energy efficiently could make partial self-charging more impactful. Advances in supercapacitors could also play a role. Supercapacitors charge and discharge rapidly, making them ideal for capturing intermittent energy. A vehicle could store self-harvested power in capacitors before transferring it to the main battery. This would smooth out fluctuations from solar or kinetic inputs. It would also reduce strain on the main battery, improving its lifespan. System-level design is crucial to achieving these synergies. Engineers must think holistically about how components interact. A poorly integrated system could waste more energy than it saves. Thermal management, for example, is a major consideration. Both solar panels and batteries lose efficiency when overheated. Designers must ensure that added energy harvesting surfaces do not inadvertently raise cabin or battery temperatures. Cooling systems may need to be upgraded to compensate. This could offset some of the energy gains from self-charging. Therefore, trade-offs must be carefully evaluated at every stage.